And so we're gonna do a video on doing long division and partial fractions. And so when are we gonna use something like this? So for example, you're gonna have a situation where let's say that forget this for now, we're gonna do that as an example later. But let's say that you had a function here. You had to integrate something that looks like this, right? Where it's like fx over gx. And like let's say that the degree of fx is larger than degree of gx. What that means is like fx is going to be like x squared plus 2x plus something, and then degree of gx, it would just be like x plus something, or like 4x plus whatever. So that's what that means. And what this is going to yield is you do long division and you're going to get a function, let's say it's lx, right? Plus a remainder rx, and then over the original gx. And you can integrate. So when we integrate the whole thing, if we were to integrate the whole thing, it's easy to integrate lx, right? Because it's just a polynomial. You can integrate lx pretty easily. But then integrating rx over gx, this is going to be tough, right? So then we have to do partial fractions, and you'll see how that turns out later. So let's say that we had the example of having to integrate x minus 2 over x minus 3 over x minus 1. My bad, guys. X plus 1. Just went to check. Okay, so when we have this, we're going to be doing long division first. So let's group x minus 2, multiply that with x minus 3. So what we have is x squared minus 5x plus 6. Okay, x squared minus 5x plus 6. And now we're going to have that divided by x plus 1. Okay, so we're going to be looking at the first one, x plus 1. What does x plus 1 have to multiply by to be able to reduce to x squared? I'm going to give you an example for it at the start. We need it to multiply by x. Then x plus 1 becomes x squared plus x, right? And we're minusing this. So this becomes 0. And minus 5 minus x is going to be minus 6x, right? Okay, next, what does x plus 1 need to reduce minus 6x? Well, we need to multiply by minus 6. Then that will become minus 6x minus 6. We're minusing this. So minus 6x minus 6x minus 6x is going to be 0. And 6 minus 6 is going to be 12. 6 minus 6 is going to be 12. So what we have here is, I'm going to rewrite it for you. Okay. What this basically says is x minus 2 multiplied by x minus 3 over x plus 1 results in whatever we found on the top here. So it perfectly got divided by x minus 6 and leaves a remainder of 12. And this 12 is divided by x plus 1. That's what the remainder is. So x 12 over x plus 1. So that's what we got here. And later on, we're going to figure out how to do partial fractions with something harder, but this is basically what's it. And now if you wanted to integrate this, you just simply integrate this. So this would simply be integration of my x minus 6 plus 12 over x plus 1 dx. And this is quite simple because this you can just convert to x plus 1, 12x plus 1 minus 1, which just becomes a ln. So this one's a simple one. I'm going to pause and find you a hard partial fractions. I'll be back. All right, so let's say that here I know it didn't turn out that way. Like here it was a simple division and it worked out, but sometimes it's more complicated and sometimes you're going to end up with a more complicated remainder. So let's say that when we did a hard thing, it leaves something like this. So there was a nice polynomial here, lx, plus, and then whatever this is. This is the remainder, right? And now we're going to have to integrate this. You also notice that this is already broken down. Let me just check. I think I might have I got it from my previous thing. I think I might have, yeah. So let's just say it was x plus 1 over x squared minus 5x plus 6, right? So let's say this was a remainder, and like this was Lx plus a remainder. So this is Rx over Px, for example, and or Fx, Rx over Fx, and it's just this is what the remainder is. How are we going to integrate this? This is not something easy to integrate, right? Like you can't just integrate x plus 1, x plus 1 over x squared minus 5x plus 6. Let me just check. I'm so sorry, guys. Minus 5x plus 6. Yes. This isn't something that you could just do straight away. You got to decompose it somehow. And that's what we're going to do. Okay? We're going to do it. And what we're going to do is we want to split this into something of a over like a function plus b over a function. And then in this case, we can integrate it, right? If we integrate that, that will just be like a 1 over f dash x. Sorry, 1 over like the integration within it, whatever. So it's going to be a Linux kind of thing. It's a lot more simple. Oh, I keep doing that. Okay. So how are we going to do partial fractions with this? Well, what we're going to do is we need to split this into its components first. So let's see, 6 minus 6x plus 1x. So we could do minus 6x plus x plus 6. Then this would decompose into x minus 6 plus 1 minus 6x plus x. X minus 6 plus, okay, not x minus 6 then. It could also be 2 times 3. So x squared minus 3x minus 2x plus 6. Then this could give us x of x minus 3 and minus 2 out of x minus 3. And this means that we can decompose it into x minus 3 times x minus 2. So we can rewrite x plus 1. We can rewrite this as x plus 1 over x minus 3 and x minus 2. And what we want to convert this into is turn it into something like a over x minus 3 plus b over x minus 2. You want to turn the fraction, the polynomial over polynomial into a sum of constants over a function. So that's what we're going to be doing. And so how are we going to do this? Well, let's just state that both of them are equal, right? Both of these are equal. Okay, now I want to multiply this up here and this up here and put them into the same fraction. So I'm going to rewrite the whole thing. Let me just copy this actually. Okay, so we have this, oh my gosh. We have this down here. And this is going to be equal to a multiplied by x minus 2 plus b multiplied by x minus 3 all over x minus 3 times x minus 2. And because these are, you see how this fraction here has the same denominator as this fraction here, that means that we can think of it as these numerators are equal. So now if we set up this equation here, where x plus 1 is equal to a multiplied by x minus 2 plus b multiplied by x minus 3, there's two methods where we can do, right? There's two methods. So I think a very intuitive one is when we consider the roots. So let's see, look at this. So we have x minus 2, right? So when x is equal to 2, what happens? Well, 2 plus 1, let's just substitute 2 into every x we see, is equal to a multiplied by 2 minus 2, that's 0, plus b multiplied by 2 minus 3. What do we end up with? We have 2 plus 1 equals 0a, so nothing, and then 2 minus 3 is minus b. Look at that, right? So we end up with b is being equal to minus 3. Another, and then we do the other root. So now we want to do x equals 3. So let's say when x equals 3, so what's that? 3 plus 1 equals to a multiplied by 3 minus 2, and b multiplied by 3 minus 3 is 0, so I won't write that. So then that would be equal to 3 minus 2 is equal to a. So a is equal to 4. Okay, so that's how we find it. We found b equals minus 3 and a equals 4, so we can rewrite x plus 1 over x minus 2 multiplied by x minus 3 is also equal to 4, let's use the same form, a over x minus 3, form over x minus 3, plus b over x minus 2, and b is minus 3. So then would be minus 3, or we can do that, minus 3 over x minus 2. And now the integration of that will be quite simple, right? It'll just be like ln x with like an extra multiplication. Okay, there's another method here, and I plan not to use this, but if there is a chance, because this is, and I'll tell you why this is good. This is, we're going to be comparing the constants. So let's have our equation again, where we had x plus 1 is equal to a multiplied by x minus 2, and b multiplied by x minus 3. Let's try multiplying everything out. So what we have here is x plus 1 is equal to ax minus 2a plus bx minus 3b. If we rearrange with all the x's, that's ax plus bx minus 2a minus 3b. Let's compare the constants. This is 1x plus 1. This is x multiplied by a plus b. So if we think about it, it's a plus bx, like that, minus 2a minus 3b. So if we think about it, the coefficient for x is this. So we can say that, look, 1x is equal to a plus bx. So therefore, a plus b must be equal to 1. And the constant is plus 1, and this is the constant there. So therefore, 2 minus 2a minus 3b has to be equal to 1. And then you can just use like substitution, or you can just use like any method to manipulate it. It comes back out as this. So there's the two different ways you can do the partial fractions. I think this method here, the second method with the looking at constants and the coefficients, this is really good when you have not just like x plus 1, but like x squared plus 3x or something, right? It's going to get complicated. And when it gets complicated like that, this is the superior method, because this would just work. You can just look at the coefficients of each x power, so x squared, x constant. Meanwhile, this method here really only works when there's like x minus x plus something, because then it turns to 0. So depending on the circumstance, you can do what you need. But this is the reason for why you want to use partial fractions, is to solve for the remainder, and that's also how you do long division and how you solve that. All right, thank you guys so much.